lists specifically talk about folds. So the most recent module that was assigned on Wednesday, if you haven't taken a look on that, I think I mentioned this, but it is posted on the website due next Wednesday. That'll give you a lot of practice working with folds and thinking about folds in general. Definitely go and rewatch at least the last part of Wednesday's class. It's one of those things that I think I pretty clearly laid out exactly what you have to do, but you're going to need some practice doing it a few times before it clicks. So definitely, as you're working on the module, go back and rewatch that as you're doing it. So today I want to talk about something that's a little bit random, but it'll get us a little bit deeper into some of what Haskell can do and how it's built, and it's a very interesting idea. So I am going to write down another one of those like polymorphic function games, right? So I'm going to start by seeing if we can implement something that has this type. And we'll start just by thinking about what this thing is and what we can do with it. So ideas, so mystery, it takes 2 arguments. So we'll call this one f, I guess. And then take this other argument, which is g. So f and g are both functions, right? And then we're supposed to return a function from a to c. So first of all, how should I go about doing that, do you think? Yeah?
Would you use function g in function f to output the a to c?
I think you're on the right track, but I mean, so how should I write that? Did you mean literally say, f implies
literally, yeah.
What was that?
Something.
Yeah, so okay. So I can't just say, that doesn't have the right type, because, right, f takes a b as an argument, but g does not have that type. G is not a b, it's a to b. So that's the right idea, I think, but the idea is, how should I start? Even if you don't know the whole thing, what are some ideas about how I could proceed? So I have to output a function, right? So how do I create a function? Yeah, I could use a lambda expression. I mean, another thing I could do is make a definition of some other function. But no, I can always make a function using a lambda. Right? I don't have to give it a name. So I can say lambda. We can call this thing whatever we want. I'm going to call it A. So this can be either confusing or helpful depending on your point of view. So, right, I have to output a function of type A to C. Right? So if I say lambda A, I mean that input to the function will have type A. So I've named it A. The reason it's possibly confusing is that this A and this A are different things. This A is the name of a type, and this A is a variable that has that type. Haskell is fine with this, like the names of things and types and the names of things, values are separate. But since it's a generic thing and I don't know anything about it other than the fact that it has some type A, naming it A actually is a pretty good choice. Because I'm not going to, otherwise if I name it X, I have to remember, oh, X has type A. if I just name it A, then it's like, well, obviously that's the thing that has type A. So, right, and then it says, look, I found a hole that has type C, right? Of course. We have to make a function from A to C, so I take an A, and I have to return something of type C. That makes sense. So how can I get something of type C to put here? Andre? Yeah, so the only place I could get something of type C is as the output of F. That's the only thing I have that can give me something of type C, because I don't know anything else about C, right? So I definitely want to say F of something. So, I mean, I think Andre said the complete solution, but even if we, let's say that we weren't quite there, right? We said, well, I don't know, but the one thing I do know for sure is that it has to be the output of F. That's the only place I can get a C from. So it's got to be F applied to something, right? But then you say, okay, well, what do I need to give F? Well, I need to give it a B, and it's actually telling you that, right? Well, okay, how can I get a B? Well, the only place I can get a B from is as the output of G. So I could say, all right, well, I better put G here applied to something. What could I possibly apply G to? I have to give it an A. I have one of those, so I can fill in A there. And I think this is what Jack was trying to get at earlier, right? Like intuitively, you're like, of course, we want to kind of plug them together so that you get an A that comes in and it goes through G and then it goes through F. And you get a C out. But we can't just write F, G. We have to do this, right? We say take an A, put that A into the function G, and then put the output of that into the function F. Right, so we're creating kind of this little pipeline. This is like, this function kind of takes two functions and like plugs them together to make kind of a longer function, right? Kind of like this. If I have like, here's my function F. F takes a B and returns a C. Actually, I should probably write them, well, yeah. Darn that Euler. Euler was the one who started using this notation for applying functions with arguments. And he really should have used this notation or something, or x dot f or something like that, because we read from left to right, right? And we think about, like when we write a type, we write the arrow going from left to right because we think of things going from left to right. So if you have a function that takes some inputs to outputs, it seems natural to write it in that direction. Yeah, like inputs on the left and then outputs on the right. Except this notation is the opposite. It has the input going in from the right and like going to the left. You see how up here, it's like the A comes in here and goes into G, and then it comes, the output of G goes into F this way. It's very confusing, but we're stuck with it. Like, these people have been using this notation for hundreds of years. So, anyway. And that's why if you look at the type of this, it looks kind of weird. You're like, why wouldn't you put A to B and then B to C? And then have A to C over here. Like, why is the B to C first and the A to B? It's because when we write it this way, like, the order of the function stays the same because the values flow through them kind of from right to left the way we write them. Anyway. So it's kind of like this, right? I've got these two pieces, right? And then mystery FG kind of makes something like this, right? It takes A, and then it goes through G, and then it goes through C. It just plugs them together into one big function like that. Okay. So this is actually called, so this is function composition. It's actually called dot in the standard library. Okay, so instead of writing mystery FG, I can actually write F dot G. The dot is, it's supposed to look kind of like the little circle symbol that you probably learned in, I don't know, middle school we often use that little small circle in the middle to denote function composition, right? And that's what this is. They just didn't want to use like a Unicode little circle symbol. So it's just dot. Someone have their hand up? Yeah.
Put is the lambda function. How do you know what the type of the input is going to be? Especially like this is this.
Here? How do we know what type this is?
Yeah.
I mean, you don't know just from looking at, like if you just look at this, well, you can't see that highlighting it open. If you just look literally at the syntax of the lambda, you can't tell what type the input's going to be. Haskell can figure out what type it is because, you know, we said mystery should have this type. And so mystery FG, well, it needs to output something of type A or OC. So if we write a lambda, like that had better be something of type A that it's taking in. Now, you know, but this A could be anything. So when we use mystery, when we use function composition, we can kind of decide what type of functions we want to apply it to. And then A will be whatever we use for that. Does that answer your question? I'm not sure if I answered your question or not.
Other than kind of like actual types, but like in the way that the function is written, where it's like B to C and A to B,
Right.
A to C, how do we know like the input's not going to be at first, like it's B to C?
How do we know? Say that again?
Like, where does the input come from? Does it come from like the A to C, like the last part, or is it when like the function B to C first?
Yeah, I mean, I think you have a good question in there, and I'm just trying to figure out what the question is.
I think it's asking like, what does the input look like first? If you're the input, that should like run the function.
I mean, we can do some examples. I don't know if that'll answer your question or not. But, maybe I'll take one more stab at answering it, and then you can, if it doesn't answer it, we can move on and see if your question gets answered later. So like we've said that this is the type of mystery, right? So it's a function that takes two arguments and returns something, right? It takes one argument, which is this B to C, and then a second argument, which is this A to B, and then the return type is A to C. Does that make sense? So then when I'm defining it, I say mystery FG equals, right? These F and G, those are the first two arguments of the function. And so I know that F matches up with this part, right? G matches up with this part. And then the output, the thing on the right of the equals, has to have this type. I'm still not confident that I'm answering your question. Okay, yeah, like, if it suddenly clicks, tell us, or ask again later, because I feel like there's definitely something important there, something I haven't explained or something you're confused about, but not sure. But so I don't know, a few examples of using this. Like, let's make a few functions just for like be able to. So like double x is 2 times x. I don't know. Or let's say like well, we also have like, you know, we have like length. That's already built in. I'm not going to write it, but I'm just saying we could have that in our minds as something we could use, right? Maybe we'll also have like maybe we'll say like. So then, so I'll write a function now, f, so just type sense what this function is supposed to do? It's not a very useful function, right? But it basically, it takes a list, it duplicates it, so like it concatenates it with itself, then it finds the length, and then it doubles that, and then it triples that. So we should get like 6 times, actually I guess we're going to get like 12 times the original length of x, because it duplicated it first, and then got the length, and then multiplied it by 6, right? But in all these states, so like, if I, so if I say f of, 2 to 7, I should get 24, I guess, because, yeah. We duplicate that, we'll have length 4, and then we multiply by 2 and by 3, we'll get. But, right, there's a different way that I could write this function. So I claim, so I'm going to write length f prime. Because really, right, what is f doing? It's really just taking an input and then running it through kind of a pipeline of functions, right? So I actually don't have to mention the input at all. I can just say f prime is defined to be the function which is this composition. So first of all, do you all agree that this, like using this operator, I mean, I guess we didn't, of course we can, so this operator composes 2 functions, but when we compose 2 functions, like the result is a function, which we could then compose with more things, right? So, so that makes sense that we can kind of iterate this. And the parentheses don't matter, because if function composition is associative, right? If I do run f and then g and then h in order, it doesn't really matter if I compose g and h first and then compose that with f, or if I compose f and g first and then compose that with h. I'm going to get the same 3 functions in the same order, doing the same thing, so it doesn't really matter. So I don't need to use parentheses here at all. So hopefully, first of all, you all agree that this does the same thing as this, right? And this is what this means. It means make a function that takes a thing and then puts it through in that order. The other thing that is interesting about this, right, is that I'm defining a function here, but I didn't mention its input at all, right? And it turns out there doesn't have to be any particular relationship between the type of a thing you're defining and the number of arguments that you happen to mention in the definition. Because rather than saying, oh, here's what this function does on an input called x's, it outputs this. I'm just saying this thing is defined to be this function. That's totally fine, because functions are first-class things. So if I have some expression that gives me a function, I could just define some function as that. I don't have to say what it does on a specific input. Okay, and I don't know about you, but to me, this is much nicer and easier to read than this. All right, there's no parentheses. I don't have to give this thing a name, because I don't really care about giving this a name. That's not the point, right? So not having to give that a name is nice, because I can just say, here's what the function does. It does this sequence of things in this order. Okay? So you're welcome to use that as you're defining things. And probably, I mean, you don't need to do this, but if you went back over the first few modules that you've done, I bet you could find instances where you're doing basically this kind of pattern, where you're calling multiple functions on a single thing, and you could rewrite it using composition. I'm guessing you might find that. Okay, any questions about this point? All right, so I'm going to reveal another mystery about mystery. In particular, so maybe you all already know this, it's a good idea to write down the type of things that you define, because that helps. If you make a mistake, it can more easily show you an error, etc. But if you leave off the type, she is is okay with that. It can just figure out, it can infer what type it has to have. So what I'm going to do is I'm going to remove the type signature. I'm going to comment it out, reload this, and I'm going to ask GHC what type it thinks that mystery has. Okay? So I want you to look at that and tell me what do you notice about that? You notice anything interesting? I mean, for one thing, it's using different letters than we use. But I mean, the names don't really matter, right? Yeah.
Just the same sequence as Mr.
Yeah, it's the same as, is it the same as the type that we gave?
Yeah.
So like T1 corresponds to what we call B. So like B is here, and then also here T1. Yeah, so T1, T2, T3, T. Yeah, it's a little. You gotta stare at it for a minute because it's like numbering them in a different order. But does everyone agree? It kind of has the same pattern of. Okay, is it exactly the same though? Alexandria?
Is it going to return a value instead of a function?
Yeah. Why do you say that?
Because in the type part, it's
Huh?
T3 to T2 instead of in type.
Right. What happened to the parentheses? What happened to the parentheses here? Right. We put parentheses here. It's returning a function, and it didn't put any parentheses here. What the heck? So, we will come back to that, but I want to tell you, like in general, what is going on. So, and this is, right, this is also getting back at, I think early on, right, we wrote down, I mean, the syntax for functions that take multiple arguments is you put a bunch of arrows in between them, right? And it was like, why is that? Why are there arrows everywhere instead of just like at the end? So we're going to learn why. So it turns out Haskell only has functions of one argument. Okay, all this stuff we've been talking about, like functions that take 2 arguments or 3 arguments or whatever, we're just kind of pretending. There's no such thing as a function that takes more than 1 argument in Haskell. So how is that possible? Right? So, you know, for example, if I have I'll just call it x, y, x plus y. Okay. So we've been calling this a function that takes 2 arguments. However, this is really a function that takes an int and returns a function from int to int. Okay, so in other words, I'm saying it's the same as this. So let's do some examples over here, and hopefully I can convince you that that's really the case. And then we'll talk more about like why or what this means. So if I say add 3, so add, right, so it shows the type like that. But I claim that add really is a function that takes 1 argument. So if I say add 3, like my claim is that it's going to take that 1 argument and then return a function as output. So like if I ask for what the type of this is, what's the type of add 3? It says, yeah, that's a function from int to int. Okay, what function is it? Well, it's the function that's waiting for one more input, and then it's going to return 3 plus whatever we give it, right? So, so this is called partial application. Some languages have partial application, but it's like they have special syntax to do it, or it's like built in specially. Haskell is not actually a special thing because since every multiple argument function really takes a single argument and returns a function, you can just do that. You can just only apply it to one argument and get back a function if you want. So for example, we can say things like, map add 3, 1 to 5. And I've partially applied add to 3, which gives me a function that will add 3 to an int. And so when I map that over this list, that works. I get 3 more than each thing. And that's actually what's happening too. And we can also, we don't have to use the function add. We could just say like plus 3. Right? This is really partially applying the standard plus operator to only one input. And it gives us back a function that's expecting the other input. And we'll add 3 to it. So let's just do that. So we can use this to partially apply functions to their. Or if it takes like, if you have a function that takes like 5 arguments, you could apply it to the first 2 and you'll get back a function that expects the other 3. So the idea of representing multi-argument functions as single argument functions that return functions is called Curried. It's named for Haskell Curried, who was a British mathematician, I think. The language Haskell is named after him as well. And it's named after him because he used it in a paper or something and clearly said that this other person invented it. So everyone named after him. So there's this other guy named Moses Schoenfinkel, who actually was the first person to come up with this idea and published it. And so then Curried used that and said, I got this great idea from Schoenfinkel. And everyone was like, great, we're going to name it after you. I don't know why. That's just, that's what it is. So, I mean, really it's Schoenfinkel, but maybe that's a little too long or something. Say, invented by Moses Schoenfinkel. But Haskell Curried used the idea and credited Schoenfinkel. But it got named after Curried. Which is pretty typical in math. If you look into like most things in math that are named after someone were discovered by someone else. I don't know why, it's just like how it works. It's like maybe things end up getting named by who kind of popularized it or something instead of who actually named it. So this explains why, like why the type of add is written like this. Right, so like this explains why multi-argument function types are written, R1, R2, right? Because it's really R1 parentheses R2 parentheses R3. Right? When you see a function type like this with multiple arrows, it really means this. So function arrows associate to the right. So that is, if you see a bunch of arrows in a chain with no parentheses, it really means just like keep adding parentheses in the rightmost place. But think of this as, and we do think of this as a 3-argument function, but really fundamentally, it's a function that takes one argument of this type and returns a function of this type. And that function that it returns takes an arg2 and then returns a function of this type. And then that final thing takes an arg3 and returns a result. Okay. This is also why, right, notice, like, think about how we write, so when we apply a multi-argument function, we write f of x, y, z. Right, so if f has this type, arg1 to arg2 to arg3 to result, right, I would apply it by writing this. Right? What does that really mean? What this really means right, it says, well, f really is a function that takes only one argument, right? So we'll apply that to x, and that gives us back a function, and we're going to take that function and apply it to y. And then that is going to give us a function, and we're going to take that thing and apply that to z. Right? So function application associates to the left, right? And that's like, that is fxy means fx. So, and the reason they're different, right? The reason that arrows associate to the right and application associates to the left, right? It all goes back to Euler and that terrible notation that he invented, so that, like, when we're writing down function application, like, it looks like values are going from right to left, and with arrows, it looks like they're going from left to right. That's why they're reversed result. But they fit together very nicely, right? Kind of the reason fundamentally is the same. So this is just a really nice idea that lets us, pretend as if we have multi-argument functions, but actually, number one, the compiler doesn't have to worry about dealing with multi-argument functions. Everything is just a function of a single argument. And number two, it lets us do nice things such as partially applied functions, just like for free, right? Which is a very nice. I mean, like, this is great, right? And there's lots of more complicated situations where it's really nice, but if I want to just add 3 to a bunch of things in a list, right, it's really nice that I don't have to put a lambda or something. I don't have to say, like, lambda x, plus 3. I can just say add 3. And I'm like, yeah, I know one of the things I want to add, and then the other things are going to come from the list. Okay. So, right, going back to our mystery thing, right? That's why it writes it this way. Because, right, when it returns this function, since function arrow associates to the right, these parentheses on the right are not needed. Right, so this is actually exactly the same type as what we did. It's just that the parentheses we wrote at the very end were redundant. Right, because saying it returns a function from T3 to T2 is actually the same thing as saying, oh, it takes one more argument T3 and then returns a T2. So, why are these parentheses needed though? So we know now that, like, A to B to C is the same as A to B to C. Right, but what about A to B to C? Is that the same also, or is that different? question is, right, so we know, right, those two things on the top are the same, but is the thing on the bottom the same as those two on the top, or is it a different thing? Yeah.
Would that be a function A, B, with output C, rather than, the top one would be, function A would put output into a function that outputs B to C?
Right, and are those different, or are they, could we kind of use those interchangeably, or are they different things?
Technically different.
Okay. I mean, when you say technically different, does that mean like, well, technically they're different, but they're really kind of the same? Or does it mean like, no, they're actually different? Which is it?
I would say actually different.
You say actually different? Why?
Because kind of how you were describing the association of the parentheses.
Uh-huh.
I think it's because the top one is the same as that one because you're reading it as like a function to the right where B is applied to C, and then it kind of moves almost right to left in a sense with your association stuff that you're kind of talking about.
Yeah.
And you obviously, and then if you look at the bottom, you're applying it as looking at it as C, and then a function over here that's not reading the same way.
Right.
So that's
Yeah.
not a great explanation.
No, but you're right though. Yes, these are definitely fundamentally different, right? The top thing says, right, it will take an A, and you can read it either as it'll take an A and a B and give you a C, or you could think of it as it takes an A and gives you back a function that will take a B and then take a C, which is the same. But the bottom one is not taking an A and a B at all. It has to take a function from A to B, and then it'll use that to give you back a C, right? That's very different. So like, to use this top function, right, what do I have to have? I have to have a value of type A, and I have to have a value of type B. And if I have those things, then I can hand them both to that function, and I'll get back a C, right? This thing on the bottom, if I have one of these, having an A and a B doesn't really help me, because it's like, no, I want a function. You have to give me a function from A to B, and then I'll give you a C. I'm like, I don't have a function. I've got an A here, and I've got a B. It's like, no, you got to give me like an actual machine that will turn A's into B's, and then I'll use that somehow to make C, right? Those are very different things, right? The other way to think about it is, right, this thing on the top takes 2 arguments. The thing on the bottom only takes 1 argument, which is a function, maybe. Right? So these, right, and that's why, right, these parentheses here are absolutely necessary. If we get rid of those, it would mean something totally different, right? Like if I get rid of these parentheses, now instead of taking a function from T3 to T1, it's taking a T3 and it's taking a T1, right? And that's a different kind of thing. It's just the one on the end that we can get rid of the parentheses, because that final function that it outputs, we could also think of it as, oh, it takes an extra argument and gives us a result. And by the way, so going back up here, so put it down here, history 2, right? So now that we know that I can get rid of those parentheses, and that's okay, right? That suggests we could think of this as, if we think of the parentheses there, we could think of it as taking 2 arguments and returning a result. But without the parentheses, we could also think of it as taking 3 arguments and giving us a C. So I can actually write it, so F, G, and then I'm going to name this argument A, and then I'm going to return F, G, A. So this is also a valid way to define this function. Before I defined it, mystery 2 FG equals lambda whatever, so there I'm like explicitly thinking of it in terms of returning a function. But I can also define it this way. I can think of it as taking those 3 arguments and giving me back a C. Those are equivalent, because really what happens is when we write this, it actually translates it immediately into a bunch of lambdas anyway, So it's really exactly the same thing. It's just like this is a nicer syntax for writing, right? It's really, under the hood, it's really, it says mystery 2 equals lambda f, lambda g, lambda a, blah, blah, blah. Right? That's really what it gets translated to. So there's not any difference. Other questions? Thinking of my water bottle, like, I'm gonna take a drink, but like, nope, can't do that. I don't know why I wrote it. Just like part of my head, maybe. Cool. So, I hope you find this mind-bending in a good kind of way. I do. It's definitely one of those things that you have to keep coming back to and reminding yourself how this works, because it's kind of a lot to assimilate, and it's there's like a lot of different ways to think about the same thing and different ways to write it, and it does kind of all follow kind of elegantly from this kind of a few simple, concise ideas, but it still can be confusing to like think about all the different ways that it manifests. But it is a pretty elegant way to think about, what functions are. Here's one other thing I can say. So, I'll make another add. So if you want to actually think about like multi-argument functions, another way you can think about it is, of course, Haskell doesn't really have multi-argument functions. It only has single argument functions. But the single argument could be a tuple, for example, right? So you could define add like this, right? And we can think of that as a 2-argument function. It's really not. It's a 1-argument function that happens to take a pair, and then that pair has 2 values. You can do whatever it wants. And it's possible to turn functions defined like this back and forth into functions defined the other way. So, so we could also define multi-argument functions like this. And there's functions. I didn't figure out how to turn this off. It's like my editor is very, very keen to turn anything I type into like a suggested thing that's in scope that has some vague resemblance to the thing that I type. I'm like, no, this time. So there's a standard function called Curried that takes a function of this type that takes a tuple to something and returns a curried function like this, right? And then also uncurried, which goes the opposite way. And these are not hard to define. They're just defined in a library. They're not built in. It's a nice exercise if you want to try to implement these. But basically, it's showing that we can represent a truly kind of multi-argument function like this we can represent it as a function that returns a function like this, or vice versa. So, you're welcome to try that, or you can just go look up how they're defined if you want. But I recommend trying to implement it first. It's kind of instructive. And right, they should be called Schoenfinkel and unschönfinkel.